All right, open up your book to section 6-6. We're on page 314 in your book, and the title of this section is Inverse Circular Relations. Given y, find x. And our objective is, given the equation of a circular function or trig function and a particular value of y, find the specified values of x or theta graphically, numerically, and algebraically. So we've looked at graphically and numerically how you solve these, and now we're going to look at how we solve these algebraically. All right, so take a look at example 4. Example 4 on page 316 in your book is the same problem we left off with examples 2 and 3. But now it says find algebraically the 6 values of x in example 2. Show that the answers agree with those in examples 2 and 3. So we already came up with the equation of this function back in example 3, so that's why it's already here. But if they had not had us do that, obviously that would be the first step, come up with the equation of this, but we've done that. Now what I want to do is I want to solve this algebraically using arc cosine to do it, and in particular finding out at the end what values of n and whether I use the plus or minus cosine inverse to find my solutions that I'm looking for. All right, let's go ahead and solve this algebraically first, and then we'll tackle the other part of this, which is figuring out what values of n and the plus or minus to pick. So to solve this algebraically here, we just are trying to solve for x. So I want to get rid of everything that's around the x, which is everything on the left side, in other words. So first thing I'm going to do is subtract 9 from both sides, so I'll be left with 7 times the cosine of 2 pi over 13 times x minus 4 is equal to, subtracting 9 will get you a negative 4 over here on the right side. The next step, let's divide by 7. So that'll leave us with the cosine of 2 pi over 13 times x minus 4 is equal to a negative 4/7. And now here's where we're going to use the arc cosine to solve this. If I have the cosine of some quantity is equal to some other number, we said in the first half of this that we could rewrite this as 2 pi over 13 times x minus 4 is equal to the arc cosine of a negative 4/7. Again, that's the difference here from how we've solved these problems in the past, that we've used cosine inverse here at this point. But again, the problem with that is that you're only going to get one solution. We want to get more than one solution. We only want 6 of them in this case, but I in essence want an equation that tells me all the solutions. All right, now keep going here, but keep arc cosine in the problem until we get to the very end. So get rid of the 2 pi over 13 by multiplying both sides by that reciprocal. So we'll have x minus 4 is equal to 13 divided by 2 pi times your arc cosine, not cosine, arc cosine of a negative 4/7. And then finally, add 4 to both sides, so we end up with x is equal to 4 plus 13 over 2 pi times the arc cosine of a negative 4/7. All right, so now here comes in that definition of arc cosine that we defined in the first half of this section. Arc cosine, I'm just going to replace it with its definition. So I'll leave the rest of this alone. 4 plus the 13 over 2 pi times arc cosine is defined as plus or minus the cosine inverse of whatever quantity you're taking the arc cosine of, which in this case is a negative 4/7, plus 2 pi n. That's if we're in radians. If this happened to be degrees, we'd be adding 360 n on the end. We're just replacing 2 pi with the degree equivalent. All right, let's go ahead and simplify this here a little bit. I'm going to take the 13 over 2 pi and I'm going to distribute it through the parentheses here. I got to take this guy and we're going to distribute it to this first term, and I'm going to distribute it to that second term as well. Now the plus or minus that shows up in front of that first term in there, I'm going to write that out front. So it's plus or minus, and then we'll put our 13 over 2 pi cosine inverse of a negative 4/7. So that's just simply multiplying by the 13 over 2 pi. Now when I multiply the 13 over 2 pi times the 2 pi n, notice that the 2 pi's are going to cancel each other out. And we're going to be adding on just 13n. Now you should recognize the significance here of the 13 in this problem. It will always end up that we end up with this quantity here at the end. The 13 in this problem is the period, right? That's what we found was the period. If you go back to the original equation, right there's that 13. That's the period. It should always be the case that you're adding on multiples of the period for that particular equation. That's what we have here. If you find you got something else and something went wrong in your solution here. All right, the last thing I'm going to do is split this up. The plus or minus is a nice way to write this in one line, but unfortunately, many times our solutions are going to show up where we use certain values of n for the plus for the third cosine inverse, and sometimes we use the minus for other values of n. So I'm going to write it this way. I'm going to write it in a piecewise form. I'll write it as 4 plus 13 over 2 pi cosine inverse of a negative 4/7 plus 13n. And we're going to figure out what values of n we have to use here. And then 4 minus 13 over 2 pi cosine inverse of a negative 4/7 plus 13n. So these are our two equations that represent all of the answers. But again, we are only looking for 6 of them. So let's go back up above here and find out what values of n we want to pick and whether we're using the plus or the minus. Again, the starting point for us is to consider what our phase displacement is. So our phase displacement here is 4, and 4 is right here. So at x equals 4, that's where I start counting with n. This is where n is equal to 0. That's where I have to figure out what value to start at for n, what value of x to start out at. And it's based on that phase displacement. So here are the 6 solutions that I see here. I've got this solution and this solution. So with n equal to 0, when I go backwards to the left, if I use the negative cosine inverse, I'll get that solution there. That's at a negative 1/2. And this solution over here to the right will be the positive cosine inverse. That's the one that's somewhere around 8.5. Those are the 2 solutions there with n equal to 0. You'll notice that there's one further to the left of that. Maybe I should kind of try to finish this sinusoid here if I kind of draw the next high point there, the next upper bound. That would be going backwards to the left. If n equals 0 is at 4, then going backwards to the left, this would be n equals negative 1. Notice that I don't want a solution to the left of that high point. I only want the one that's off to the right. So off to the right, the solution here is going to be the positive cosine inverse solution. And then moving to the right now of n equals 0, this would be where n is equal to 1. If I move to the left of that high point, that solution that I see there is the negative cosine inverse solution. And off to the right, the solution is the positive cosine inverse solution. And I guess I need to finish off a little bit of my function over here, a little bit of my sinusoid. We won't worry about sketching the whole thing, but we hit a high point there. If I continue moving forward one period, that's 13 units that I'm moving forward each time here for this function. This would be where n is equal to 2 to do that. And again, I don't want a solution to the right of this, but I do want the one that's off to the left. That solution right there would be the negative cosine inverse. Again, notice that you go to the left to get the negative solution, to the right of the high point to get the positive solution. So now, notice that the values of n that I need to get my positive solution. So here's a positive solution. That's going to be with n equal to negative 1. Here's another one. That's with n equal to 0. And here's another one, and that's with n equal to 1. So for the positive solutions, I need n equals negative 1, 0, and 1. So I'm going to add that down here. So for the positive, I'm letting n equal negative 1, 0, and 1. That's the values that I'm plugging into this value of n right here. If I plug those 3 numbers in, I'll get those 3 solutions. The other half of my solutions, For the negative cosine inverse, let's do that in a different color. So I see that there's a negative solution that's with n equal to 0. Here's a negative solution that was with n equal to 1. And here's another negative solution that's with n equal to 2. So I need 0, 1, and 2 for the negative. So for the negative, for subtraction here, I need the n is equal to 0, 1, and 2. You'll notice that I'm using different values of n for this problem to get those 6 solutions. Sometimes the values of n turn out to be the same, sometimes they're different. This is why we were splitting this up into this piecewise form is nice. And again, those are the values that I'm plugging into this value of n right here to get my 6 solutions. Okay, so let's double check that. Let's grab our calculator and verify that these are in fact the 6 solutions we expect to get. Alright, so with our calculator now, let's try this out. And we're going to just go from left to right there. And again, it's not a case of I'm just guessing what value of n to plug in, or whether I'm choosing the plus or the minus here. I've now gone through carefully and determined what solutions I'm going to use here to get my 6 answers. So the first solution, starting on the left, was with n equal to a negative 1, and I had to use the positive cosine inverse solution. So let's put that in here. So it's the cosine inverse of a negative 4/7. Oops, sorry, I'm missing the first part of this here. It's 4 plus 13 over 2 pi. And the 2 pi does need to be in parentheses, otherwise you're going to divide by 2 and then multiply by pi, and that's not going to be correct. And then cosine inverse of a negative 4/7. And then add on your 13 times n, and again, we're starting out at n equals negative 1. So that's our first solution there. We're using the plus in front of the cosine inverse, and we're using n equals negative 1. And we're claiming that that answer should be around negative 4.5 is what we came up with graphically, and even that negative 4.491 was our approximation numerically. And now if you move to the right, the next solution we should have there is with using subtraction, the negative cosine inverse, the opposite cosine inverse, however you want to say that, and with n equal to 0. That should give us a negative 1/2, which is what we get. And now the next solution that we come across, using the plus, and with n equal to 0, this was a solution somewhere around, 8.5 was the next one. There, we got it. And the next one should have been around 12.5. And so that's using the subtraction, or the opposite of cosine inverse, with n equal to 1. And that's 12.5. And we can go ahead and get the last couple here. Let me just make a copy of this here, though. Let me grab the last 2. So that's the positive cosine inverse solution, but now n is 1. That was at 21.5, and the other one should be close to 25.5, and that's the negative cosine inverse. Well, I guess we can do that. And n is equal to 2. That one. And there we go. Grab a screenshot of that as well. And our answer, by the way, we'll leave that in the form that we have algebraically. I'm just checking on my calculator here to make sure that we, in fact, are getting the 6 solutions that we expect to get. And our calculator is, in fact, backing us up here and saying, yep, the 6 solutions you have listed there are, in fact, the 6 solutions we should have. Again, a couple of things. First of all, you should be able to go through algebraically and solve that equation just like we did. Go through all those steps to solve for x. Even split this up as a piecewise function like we did at the end. And at the end, given an accurate sketch of this, you should be able to determine what values of n you're going to pick for each one of these equations, whether it's the positive cosine inverse or the opposite cosine inverse, and come up with all the solutions that you want. Again, it is not a game of just guessing and checking with values of n and pluses or minuses to figure out what are our solutions. If you need to go back through that example and look at it to make sure you understand that process, then do so. But you should understand how to find all of these solutions and write it algebraically like we have on this last line. Again, the piecewise form that you see here, let me put that in a box here. This is our answer right here. When it says solve this algebraically, this is how you will be leaving your answer. All right? We checked it on our calculator, but this is not what I'm looking for when I say give me an algebraic solution. That was nice to check it and verify it was correct, but that is not the algebraic solution. That right there is a numerical solution. All right. That's the end of the second part here of section 6-6.